Hi, good morning. I'm going to be talking about LEDs and eyeballs today. So I am not an expert in either of these topics, but during the pandemic, I discovered building hardware and electronics. It all started with a kit to assemble this clock. I didn't really know what I was doing, but I was fascinated and I loved looking up what every piece was and trying to understand as I put this together. I've worked in data and technology for a long time, so I've written a lot of code that's in web apps, websites, data pipelines, but they're all a little abstract. And when I close my laptop at the end of the day, it's not tangible and in my living room. So this was magical to me and led to all kinds of ideas, most of which I haven't built yet, but I'm diving in to create interactive physical things. And most of them for me come back to color. Unfortunately, turns out this was a little tricky and I was really confident that was going to be an easy part and I definitely ran into trouble. So today I'm going to share with you a quick refresher on the basics of LEDs, where I ran into trouble, 3 specific spots, and then what I learned on my journey to understand. So this is a RGB LED. And you may have seen them like this as well. They're very common today in strips. And if you get the right kind, you can control each of the LEDs individually, setting brightness or color. But all of these, whether the former or the latter, actually have 3 lights inside every LED, a red, green, and blue. Turns out this is all you need to make millions of colors. So I hooked up. This was my first time hooking up my RGB LED. I'm ready to go. And this is how you set values, not the color picker on the right, but setting values for RGB. It's typically a number between 0 and 255, and you would set that for red, green, and blue. That's because one 8-bit byte holds 256 integers, or 0 to 255. So that's the way we've always stored these values. And it lives on in color pickers like paint and other things you see. So I'm ready to go. I'm ready to move through my millions of colors, and I think I'm going to hold brightness or luminance steady. And so this should be easy, right? I'm just going to slowly decrease red as I increase green, and so on and so forth. And I think as I do that, I'll get this nice color fade. I'll do the same with green and blue. So here was my code, pretty simple. Every 5 milliseconds, I am rotating through and I'm going to be decrementing one color until it's 0, while I increment another color until it's 255, then switch to the next set of colors. So this definitely gave me some glowy gradient, but it wasn't quite what I expected. The weirdest thing is it seemed to pulse with lightness at different times. I thought I was holding the brightness steady. So the brightness seemed to vary when I was only trying to change the hue. So, okay, well, these colors kind of looked washed out. How can I get the colors I really want? Well, there's all kinds of RGB color pickers online. And as you can see, they're not all constant brightness. To create navy or dark blue, you need to have much lower values. This was my first clue that brightness is intrinsically tied to color and you can't separate the two. And this means there are a lot of optical illusions where 2 colors that appear to be the same brightness, if you grayscale them, they're drastically different, but it's because of how we perceive brightness for that color. So at the end of the day, it was still hard to create the hues that I expected. And so I started building more clocks. I was on this path to build clocks, and I've used a bunch of different digits. These are, a maker built these, and they're on rgbdigit.com. You can find them on Tindy, different people putting together RGB LEDs into different combinations of digits. And I wanted to do these beautiful gradients. So maybe at sunrise every day, there would be some kind of animation, and the clock could be bright, vibrant blue colors during the day. And overnight, so it wouldn't screw with my night vision, it could get deep red and orange. So I did a lot of manual color picking, but at the end of the day, I programmed the clock during the daytime and I just scaled everything down linearly to the brightness I wanted at night. And it didn't look good. There were things that the color wasn't what I expected, or where I had a refresh rate where I was updating the color. You couldn't perceive it with the naked eye at all when it was bright. All of a sudden at midnight, I could almost see it flickering. What was going on? So there are libraries that fix this, but I want to talk a little bit about what the problem was, because it wasn't my code and it wasn't my hardware, which I did wonder for a moment. Turns out this is actually how we perceive color. One note that as much as 1 out of 8 men and 1 out of 200 women have some type of color blindness. And so while that's important to remember, certainly for design and communication, there may be folks who don't see this presentation the same way I might. So here's what I remembered about the eye. There are cones and rods, right? And this is how I imagined them. And even though there are millions, I'm like, okay, these are sticking on the back of my eye. And that's about as much as I remembered. Well, it turns out rods actually look like this. And there are around 120 million of them. And there are around 6 million cones. I also had imagined, and oftentimes you'll see it oriented this way in papers or books, that the cones and the rods were the thing the light was hitting first. Turns out that's upside down, and the light actually is passing through this layer of nerves and nerve cells before it gets to those photoreceptors. They're also not distributed evenly. Right in the middle of our eye, we have a really extreme density of cones, and the rods are more in our peripheral vision. My favorite way to play with this, if you haven't tried this, is when you're looking at stars, you can often find a star in the sky that you can see it out of your peripheral vision. If you look straight at it, it disappears. Look just to the side, it reappears. And that's because it's too dim for your cones, which are in the center, but your rods, your peripheral vision, can see it. So one thing to know about the cones, these 3 photoreceptors we have in the back of our eye, is that they are sensitive to different ranges of wavelengths of light, and they even within those have different sensitivities. And this is part of what explains that glowing brighter, glowing dimmer effect I saw when I was blending linearly through the colors. The trichromatic theory explains why these 3 types of cones in our eyes can see millions of colors. So if we have orange and an orange wavelength is coming in our eye, it's going to excite the red cone, the long wave sensitive cone, and what we often call the green cone, the medium sensitive cone. These are made up numbers. Let's call this percent excitement. But let's say it's going to excite that long wave cone around 50% and the short wave cone around, or the medium wave cone around 10%, and it doesn't hit that short wave cone at all. That's orange to our eye. 50% excitement of the red cone and 10% excitement of the green cone, that equals orange. That means that we can recreate this lots of different ways. So to create orange in the RGB LED, we would be putting in a lot of red and a little bit of green, but to our eye, that equals the same thing. So I'm not going to go into the details on this, but part of what I found fascinating was metameric colors are colors that don't match the actual wavelength on the spectrum, but are built different ways. And you can definitely go into a deep Wikipedia hole on this, but there's all kinds of interesting failures where you match colors under certain conditions, but then if you look at it from an angle, illuminate it with a different light, you can actually see it differently. There's one more theory that's really important to understand, and it explains how we see an after image. If you've ever seen those optical illusions where you stare at the thing on the right and then you look away to a white screen, but you see the thing on the left, that actually is happening because of how our photoreceptors are connected to our optic nerve through these bipolar cells and ganglion cells. They actually kind of work like logic gates. So all cones can provide input into luminance, but there are 2 separate systems called the opponent systems that help those nerve cells actually interpret what it's getting from the cones. So we can either perceive excitement as red or green. We can't see both at the same time on that particular group of cones. Same thing, we can see blue or yellow systems, but not the same at the same time. This is why you can see reddish blue, but you can't see reddish green. It actually turns out that a lot of color is really dependent on context. So here, the top center square and the front center square are actually the same color, but our eyes are really good at trying to figure out what the lighting conditions are and then making assumptions based on that. Here's another, A and B are actually the same color. And even when we connect them, it's hard for me to believe that. I almost see that as a gradient. Color can also depend on the language you speak. Some cultures have more names for something that we might think about as light blue or dark blue, or less names, and folks will actually see those as distinct colors or associate different meanings with them where we may not see the distinction. So back to the problems I had, brightness seemed to vary when only changing the hue. It was hard to create the hues that I expected, and things that looked good when bright were bad with dim. The stuff that I learned is that perception of hue is tied to luminance and context, and you cannot disentangle those. Our perception of brightness is not at all linear. Our eyes are much more sensitive at low lights because of the cones, and not all humans perceive color the same way. So a couple of things we can do to fix these. The first is gamma correction. So this is linear intensity, but to my eyes and likely to yours, the step between 0.0 and 0.1 seems to be a lot bigger jump than from 0.9 to 1.0. So if we scale intensity on a logarithmic scale, we can get it to look linear to our eyes, even though it actually isn't. Humans have also tried to solve for blending colors by creating color spaces. So if you map RGB onto a cube, you can get this. The problem is it transitions between the colors won't actually look linear to the human eye. The color wheel picker is really popular today too. There's HSL and HSV. That's another way to pick color, but it's also linear in a way that makes sense for RGB, but doesn't make sense to our eyes. So there's been color standards, committees, official government colors, all kinds of ways to try and get us to agree on what yellow is yellow. Tests that we've run to display lights of different colors and have people say when they're accurate. And then there are color space development. So the International Commission on Illumination created a color space in 1913 that's still used today. It's 3D, and it allows us to measure the distance between two colors and to plan a path to fade between two colors in a way that looks a lot more linear. If you take away the brightness dimension, you can look at this in a 2D space. And when you map the RGB color space onto the C-Lab color space, you can actually see that the RGB didn't look very linear to the human eye, and this is a better attempt to do that. One final color space, and this is a new one. It came out in 2020. You can Google it, and if you just Google OK Lab color space, you'll find it. There's a lot of ways to engage with it in different programming languages, but it has 3 variables, but it works on predicting how to fade color, how to translate color in a way that is going to match human perception. So here's the rainbow gamut using OK Lab, and on the bottom is using that hue saturation value, which actually doesn't look like it's holding a constant lumosity to the human eye. It also helps you blend in between colors without getting too warm or too cool or blending too fast. So at the end of the day, what I'm now doing when I work with LEDs is I'm making sure I do gamma correction for the nonlinear perception of brightness. I'm still manually fine-tuning to pick my favorite hues, that exact color of purple or red that I want, but I'm using a color space model to figure out how to fade between colors in a way that's going to look good. I am testing separately in different lighting conditions because stuff just gets weird when it's dim. And in a lot of my designs, I'm thinking about how would this look like to a colorblind person? How would this look given some of what I've learned around cultural significance of color? At the end of the day, I know a brain is not a computer, but I've started thinking of these rods and cones more like sensors. They have a set of inputs they work very well for. They also have limitations. And then all of these cells they're connected to before they even go to your brain is like a microcontroller with some logic on it. At the end of the day, that impacts how we can see color, gives us this incredible adaptive ability, and lets us do really cool stuff with LEDs. Thanks for listening, and I'd love to connect with you either on Discord or Instagram or Twitter if you have any questions. Thanks.